Hello, welcome to another module of this course, Microwave Integrated Circuits. We are in week 8, and in the previous modules, while we were discussing active circuits, we have discussed the various aspects of amplifier design like gain, noise, then matching. Yet another important aspect of amplifier design is the DC bias. Now, in amplifiers, both the input and the outputs of amplifiers have to be supplied with a certain bias voltage. Bias voltage means they are the, if you take the average of the inputs, then if you compute that average, then the voltage value that you get is the bias value. So, it is like the DC value or the average value. And the reason why these voltages are necessary at the input and output is because unless you provide a sufficient DC bias voltage, the transistor, the internal action, the internal physics of the transistor will not work. So, it is not just enough that you input a signal that you want to be amplified to an amplifier, it is also necessary that you provide the proper bias voltage. So, how do we achieve this? The purpose of this module is to explore the various bias topologies and how to provide the required bias. Also, later in this module, we will be covering the frequency compensation part of amplifier design. That is, we saw that the gain of an amplifier is dependent on its S parameters, but then the S parameters themselves are specific for a particular frequency. That is, if you change the frequency, the S parameters also will change. So, how to keep the gain constant even when the frequency is changing. So, that is what we will explore in the later part of this module, but first the bias network. So, the purpose of the DC bias network is many. First of all, it selects the operating point fine. So, operating point means if suppose our transistor has a characteristics without specifying what kind of characteristic this is. Suppose the characteristics is like this for various in control voltage variation, say this is V control 1, this is V control 2 and so on. Now, setting the operating point means it means you fix the point or the basic voltage input, and any further voltage input will be over and above this particular point. So, the variation will be about this point. Okay. So, that is called setting the operating point. Then the other purpose is stabilizes. The DC bias network also stabilizes transistor operation against variation of temperature. So, what happens is these, if we go back to this same curve, if suppose at temperature T1, this is the characteristics, when the temperature changes, the characteristics itself might shift. So, in that case, if you want to get the same kind of response, then your DC bias point also has to shift. If had you not had any DC bias network and if you only dependent on the AC input, then the shift could not have been done. So, DC bias, so if the temperature changes, to compensate for the change characteristics, you might want to change the DC bias point. Then there is yet another purpose of the bias network. It is that we do not want mixing between RF and DC signals. So, the DC bias network, the third application is separates DC and RF. Okay. So, DC and RF separation means that see, ideally the bias network that you should use should be something like this. This is a very high inductance value and this is a very high capacitance value. So that it will allow only high frequency to pass through this, it will not allow any DC to pass through it. Similarly, because of the high inductance value, it will not allow any RF to pass through it and it will allow only DC to pass through it. So, that is the basic. So, at the output here only DC is coming and here only DC is coming from this side and RF is coming from this side and the two are mixed. So, separation means that you have a different, you have a separate DC supply, you have a separate RF supply and they are the two networks are not interfering with each other and that is achieved by this bias network. Then it also and finally, one final use of this DC bias network could be it implements power supply decoupling. What it means is that any suppose you have a DC supply here and you connect it to this is the say the terminal which supplies power to our transistors in our amplifier. Now, any surge in the DC input voltage without a DC bias network or without this decoupling inductor will create problems for this amplifier. So, it also kind of isolates any surge in the input DC to the output. So, this is our basic DC, so ideally any DC bias circuit should be like this. If I can draw it again, there is a very high inductance value and there is a very high capacitance value. And my output will be RF plus DC. This configuration is, by the way, known as a bias T. Now, the previous example was an example of what we call a passive bias network. And in some cases, we need what we call active bias circuits. So, what is an active bias circuit? An active bias circuit is a circuit which produces a particular bias voltage irrespective of any changes in the circuit or temperature or other voltage variations. This is an active biasing network. First, let us see the qualitatively how does this circuit work. Now, if suppose this IC2 for some reason, say the IC2 changes and increases. Now, this IC2 directly goes into is the collector current or collector emitter current of this, I beg your pardon, the emitter current of this transistor Q2. If IC2 increases, then the voltage across R3 will increase. If the voltage across R3 increases, then the voltage drop across the emitter here, across the emitter collector terminal for this transistor Q1 will reduce. If the voltage, if this current through the emitter and collector reduces for Q1, then this current, note that this Q1 output current from the collector terminal, it feeds the base of Q2, and because now this emitter current is less, the total current going into the base of Q2 will also be less, and so since the base current is low, automatically the collector and emitter current of Q2 will also reduce. So, IC2 will also be reduced. So, it is like a self compensating circuit. Now, the collective, now quantitatively, if we analyze this circuit, then the value of IC2 that we get is this, where beta 1 and beta 2 are the current gains of transistor 1, transistors Q1 and Q2 respectively. Now, from this formula what we see is that for large, if beta 1 and beta 2, that is the current gains of Q1 and Q2 are quite large, then this IC2 will reduce to this value, which is independent, which is a constant value. So, by this feedback mechanism, we ensure that the total collector current flowing into Q2 is constant. Thank you.